The only reason I'm not pushing it faster is because my high voltage is connected to the inverter here with some of the cheapest crocodile clips that I could find on AliExpress. So I'm only putting about 2 to 3 amps DC through the whole system at the minute, because those things, I don't fancy our chances if they let go. Yeah, Elon sure likes a bit of regen, doesn't he? Hello folks, and welcome to the Boredom Factory, where boredom is our profession. So, as you saw in that little clip there, or perhaps didn't see, we have regen working, and also we have the inverter working at nominal high voltage, so around 330 volts was on the battery that you saw working there. So you might say, hang on a second, Damien, didn't you promise us that you were going to give us a video on the car with, you know, the inverter in the car and wired up properly? Well, that's true, I did. And I had it in there, and I was getting all set up for you good folks to show you that. And I got a full 360 volt battery in the car now, just temporarily, and I began to run some tests to see the wheels spin. Well, the wheels didn't spin. Instead, the inverter started tripping out. So, long story short is I spent about a week, had to get the inverter back out of the car, had to do some more investigation as to what was causing the problem. The inverter would run perfectly fine up to about 75 volts. Much above that, then strange things started occurring, and much above that it just shut down instantly as soon as the throttle was pressed and PWM generation started. So what it ultimately ended up being is that, yeah, I screwed up again. There were some missing tracks and missing parts and various things like that going on. So I ended up then bodging in wire links and some capacitors, and that resulted in everything settling down and working fine. As a result of that investigation, I learned some more things about the operation of the OEM board, and also then translated that into the V3 that you see here. I'm eternally grateful that I hadn't ordered the V3 until I discovered these problems in the V2, because then I wouldn't have just had one scrap board, I'd have had 10, and that would have been bad. So what I thought I would do is, here, I had promised you guys a few weeks ago a kind of a deep dive into the electronics side of things here. So I'm going to do that here now with you, and we'll kind of touch on some of the problems that I had encountered and how ultimately going back at my OEM board and doing some more reverse engineering led to the solution. And yeah, it's embarrassing to tell you the truth, but I'm hoping and I'm quietly confident that where we stand now is that I'm going to be ordering 10 V3 boards. I'm not going to put the V2 back in the car now, because it would just be silly, on the grounds that I would then have a V2 in the car and I'd be putting V3s out there to people to run tests for me, and it'd make troubleshooting a lot more difficult. So I'm going to hold off on the car and we'll put a V3 into the car. So we're going to get 10 boards from JLC. I'm going to have one in the car, I'm going to have one on the bench unit, that's going to be the destructive testing board, and we're going to have one on another bench unit, but it's a front drive unit which has the induction motor in it, but it'll be the same board, just different software. So that'll be 1, 2, 3 for myself. I'll probably keep a spare one for myself, but that'll leave me then 5 to 6 boards that I want to get out there to some beta testers, and we can start then hopefully getting a bit more real world feedback on this thing, and get closer hopefully to being able to release it to you good folks. So okay, if you're wondering what this thing is, this is one of these little beanbag heater pad type of scenarios that I have to have on me here when I'm sitting at the computer for any length of time, just due to neck pain and things like that. So I kind of find I put this in the microwave for a minute and put it on my neck. It just helps stop my neck from locking up and weird things like that. But anyway, into the circuit diagram we shall go. So let's see, where's my circuit diagram? Bring it over to you folks. Alright, so this is the V3. It is designed in KiCad 9, which I'm again slowly kind of getting to grips with it. It's got its little quirks. I used to be a big fan of Design Spark PCB, because I had learned what was the name of it? In one of my jobs I had learned Easy PC, and Design Spark was basically Easy PC with a badge on it. But they went to this, I don't know what the right way to call it is, this thing where it needs constant internet connection and all this kind of thing, all the kind of stuff that Lewis Rossman talks about. So I just decided that wasn't for me, and you know, old dog, new tricks. And here we go, KiCad. Alright, so I'll gloss over the simple stuff that I've discussed with you before, like the power supply and things like that, but I'm going to focus in on 1 or 2 changes that we're making on the V3 board that does affect the power supply. So let's zoom straight in here on our 5-volt generator chip. So this is our XL1509-5. Now up to this point, the pin 4 here, which is the on-off pin for the main 5-volt chip, was just tied to ground, so it was always on. You basically switched on and off 12-volt power to the inverter, as with all open inverter boards, either with a key switch or with your VCU system, whatever that may be. Now most OEM boards don't work that way. For example, here this is an OEM Tesla SDU board, and this has 2 12-volt feeds on it. It's got what they call a terminal 30, which is a permanent 12-volt feed, so it's just connected to the battery via a fuse, and then it's got a terminal 15, which is basically the ignition on position. Now what it basically does is it will always have that 12-volt feed there, but then you can control the wake up and the shutdown of it by means of turning on and off the terminal 15 or the switched ignition feed. So I decided that I wanted to implement that in the Model 3 board. I'm going to implement it in all my designs going forward. And the main reason for that is that what I don't want to have is a situation whereby we just dump the 12 volt power to the inverter anymore. I want the inverter to be a little bit more in charge, excuse me, about how it shuts itself down. So basically what happens here is we've got two just small signal NPN transistors. One of them is connected to the microcontroller, and one of them is connected to the terminal 15 input circuit. So basically when we turn on the permanent 12 volts to our board, nothing happens. When we turn on the switched 12 volts, which I'll herefore refer to as terminal 15, it's going to turn on this transistor here, Q17, which is going to pull pin 4 down to ground, turn on the 5 volt supply, bring everything else up, bring up the microcontroller, and so on. The microcontroller will then enable this pin here, which will then enable Q16, which will also pull that pin to ground. So what this means is, if you flick the ignition on, you flick it back off, the microcontroller can decide, is it safe for me to shut down? Have I, you know, turned off the PWMs? Is the motor stationary? Is the HV discharge? Blah blah blah, and then it can decide to shut itself down by simply switching off Q16. So there's a few extra bits to that. These two transistors here control the main 5 volt regulator, and if we come down here to our little DC-DC converter, which provides some of the isolated supplies, we have Q14 and Q13 here for controlling that now, rather than just tying that pin high. Or sorry, tying it, yeah, tying that pin high. Then basically the microcontroller can decide when to turn this guy on and off in conjunction with our main gate driver power supply chip here, U6, and that's controlled as in previous iterations via the microcontroller and via Q12, just another small signal NPN transistor. So that's our terminal 15 system, and there'll be obviously some software to put in there to support that, but it is something that I want to do because I just, particularly as the inverters are becoming more complicated, I think it's just better to have a way to shut them down gracefully, or let them do a controlled shutdown rather than just turn off the power. Now you're welcome to, you know, completely disable that system if you wish. In your application you can just tie terminal 15 and terminal 30 together onto a switched feed. It's entirely up to you. But I'm going to be basing it working on the terminal 15 system. Okay, so that is kind of a voluntary modification that we made to our power supply circuit. So next thing is it's another voluntary modification. We'll start here with the digital inputs. So we'll just pick one of them because they're all going to be the same. So this guy here, for example, this is our new terminal 15 filter circuit here. It's pretty much standard voltage divider, filter, capacitor. 12 volt input gives us then a signal to the microcontroller. But All of the digital 12 volt inputs now have one of these bidirectional transorbs in there, and that's just to provide a little bit more robustness for voltage spikes, transient, static, that kind of thing going in there. So all of our digital inputs have this one, the SMAJ18CA, and our throttle input is over here, which is obviously a lower kind of a voltage system going in, has a unidirectional SMAJ7 transorb on each throttle input. And then if we go over to our connectors, our 5 volt output, this little fuse symbol here, this is actually a polyfuse, so it's a little PTC resettable fuse. I think I've rated at 250 milliamps or something like that. So if we get a short on the accelerator signal, it won't crowbar the whole 5 volt line onto the board and maybe cause some damage in there. It'll just pop that little PTC fuse until the short circuit is removed. So again, I'm just running through these kind of, you know, these were planned for the V3 anyway, but just thought I would put them in there. Now let's get down to our gate driver circuit here, and we'll get into why the multiples of why we were having problems when we started to run on high voltage. So STGAP 1AS gate driver chip. You may recall that on the V1 board I had foolishly not connected pin 16, which is the sense pin here, to ground on the device on the high side. So that meant that every time the board powered up, even if there was no PWM going on, we got DSAT trips. So we fixed that on the V2, and then we'd no more DSAT trips. I thought, oh yay, brilliant. But then as soon as I started trying to run the inverter on high voltage, guess what? All 3 high side drivers started doing DSAT trips. So all back out of the car, back on the bench, as you saw. Went back at my OEM board and decided to see what, if anything, that I had missed out on. So yes, I had. So pin 19, the VCE clamp pin, on both high and low side on the OEM board, was connected not to ground but to VL, which is the low side, which is the low, not the low side rather, but the low switching voltage, which is -5 volts on both the high and the low channels. So basically, yeah, on all 6 gate drivers, pin 19 needs to be wired to VL. So that was one link wire that I had to put on there. I made doubly certain that the only other pin that wasn't connected, pin 22, which is the clamp pin, the Miller clamp, absolutely not connected. And I got in there, took a chip off, got a scalpel in there and literally peeled the pad off, and you know, got in there with as much zoom as I could to see if there was anything going anywhere, and there is not. So I'm reasonably confident that that's a no connect on the OEM board. So that's fine, you might say. So we did that shorting link on all 6 gate drivers, and then I could start bumping the voltage up. But guess what happened then, folks? Once I brought the voltage up and I pressed the throttle to give myself some PWM, no, we kept tripping off. This time we did not trip off on gate driver DSAT. We started tripping off on open inverter DSAT. I thought, well, that's a bit strange, because open inverter DSAT is just a pin on the microcontroller. It's not connected to anything on this board. And then, yes, that's right, folks. So let's come up here. Where's my DSAT? There's my DSAT. So my DSAT is on PC9. And you will see now that I have a 1K resistor, R98, tying that up to plus 3.3 volts. Guess what's not on the V2 board? R98. The pin was just sitting there. And of course, when you bump the voltage up, now you've got greater voltage gradients going on across the board. So any pin that's kind of floating in the breeze is going to be saying, some voltage, yes, I'll have that, or ooh, a ground, I'll have that. And it was randomly tripping. So, bodged in a 1K resistor. Confident then that all problems had been resolved. Connected everything back up, pressed the throttle, pop, off. This time it's not gate driver DSAT, it's not open inverter DSAT. It's our old buddy that many people have struggled with, myself included. It's overcurrent, yes. Clickbait video title. Bleh. So, let's go down to our overcurrent circuit here. So very quick, I suppose, what would you call it? Update on this for people that may not get it. Open inverter overcurrent circuit has been around since Johannes invented the thing. It's basically a quad comparator, LM2901, that creates a window depending on what the occur setting is on the web interface parameter database. And when you add more current, you just open the window so that the current sensor voltage can swing within the window. And if it goes outside the window, either below it or above it, I'd need 3 hands to do that. It basically causes the comparator to pull low. That sends a low pulse into this NAND gate here, which then trips the BK in pin on the STM32 and shuts down all of your PWM. So, even, you know, today, I don't know, but I still went at it. I still started messing with the window comparator and changing parameters and stuff, but no, ping, ping, off, 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 off. So, got the silly scope and I started probing. So the first thing I started probing on were my current sensor inputs to the comparator. And there were some very fast transients on there that the scope could barely catch, but they weren't there long enough to cause the comparator to trip. So then I started probing out here on the outputs of the comparator. And I realized that it wasn't the comparators tripping. See this lovely long track here going all down to the comparators and then over to the NAND gate, and this kind of a nice lazy 4K7 pull up there to plus 5 volts. That's bad when you've got 300 plus volts across your PCB. Do you guys ever see that video? I know it's bad, but it is funny. It's like some kid is on the phone to tech support and they're telling him to put his laptop battery in the microwave and wrap it in tin foil and things like that. I kind of feel like that kid with this board, and that Elon is the tech support guy. He's going to tell me to rub butter on my laptop or something next. Okay, so C2 to the rescue, 10 nanofarads. Now 10 nanofarads is going to become a bit of a theme here. because Elon on the OEM board, which of course I don't have here, I have an OEM STU board, which is not what we need. I have an OEM Jag board, Jag, which is not what we need. Anyway, they're big fans of 10 nanofarad caps. More on that later. So 10 nanofarads to ground will not overly affect the operation of the window comparator, but it most definitely got rid of, you know, like 200 nanosecond spikes on there. I confidently, yeah, this is a team too, so I confidently then kicked everything back up, press the throttle. Now this time the motor turns, but it draws loads of current from the high voltage. It starts heating up the heatsink, and the motor growls angrily, kind of turning slowly like that. Between the neck pain and, you know, everything else, I just said, "Ah, damn you, Elon!" and I just mashed the throttle pedal all the way down. At which point, actual DSAT fires on the gate drivers. So those gate drivers are really good, by the way, at saving the transistors, even from angry idiots. So it was as well that I did that, though, because I was like, damn you, Elon. We tripped off on DSAT on the high side, but the low side drivers gave me a error that I hadn't seen before. ASC. I thought to myself, oh, you've got to be kidding me, not another pin that I haven't dealt with here. Well, what is ASC when it's at home? ASC, according to the data sheet for the gate driver, is asynchronous stop command. Now that's a very I don't know what, it's just a very kind of a not very helpful phrase. It's also described in some documentation as active short circuit, which begins to get you a bit nearer to what ASC does. The ASC pin on the gate drivers, let's get you in on a high side gate driver here. Now on all the high side gate drivers on the OEM board, that ASC pin is just tied straight to ground on the device, okay? It doesn't do anything. But on the low side, see, all the low side ASC pins are tied together. Now you might see I have a 0 ohm resistor here. Now, guess what? That wasn't 0 ohms on the V2, that was 10k. So all of them, all of my low side drivers have this ASC pin tied together and a 10k resistor here. Because ASC pin, when you assert it or pull it high, basically takes over the function of the gate driver. It ignores whatever your PWM may or may not be doing. It ignores most errors. Some of them it will respect though. It ignores even if there's no logic side power. And it basically turns on the goldarn transistor. Yeah. So I'm looking at this thing, I'm trying to read up on it, and I'm looking at what it's doing on the board. I'm thinking, that can't be right. I mean, imagine the scenario. I'm cruising down the motorway. You know, got my glass ceiling in the Tesla, and I'm like, or maybe I'm on the old autopilot and I'm snoozing, or I've got a, you know, I don't know what I'm doing. Scrolling on my phone, whatever you're not supposed to do. And then for some reason best known to itself in its logic, the inverter decides activate ASC mode. Right. So you're now taking the 3 phases of a permanent magnet generator and short-circuiting them. I'll let you folks figure out what would actually occur there. It does, however, explain to me a little bit more, or help my thought process about what that HV derived power supply and all that little logic and components up in the top right hand side of the PCB is for, because guess what? Yeah, that's where that ASC pin connects. But we'll come back to that with a graphic demonstration in a later video for you folks when we're doing the destructive testing. So anyway, as a simple solution to my ASC problem, I basically swapped the 10k resistors for 0 ohms, or a short circuit. This time, I crossed the fingers and I push the throttle, and the motor spins, and it's spinning smooth, and it's pulling like 100 milliamps, 200 milliamps from the high voltage. I'm like, yes, and I'm just, you know, just getting that yes built up on me, and the next thing there's a clang sound, and the motor gives a bump on the bench and comes to a horrible stop. I thought, great, Damien, you've just blown the inverter. And indeed, yeah, there's a DSAT trip. So reset everything, and I go back at it. I try to spin it, and the motor's all kind of shuddery and jerky and drawing weird amounts of current and that. This one's on me. Well, all of them are, but this one's really on me. I had a 12 volt battery powering my test bench. Also runs the oil pump on the drive unit. And I've been running this all day. 12 volt battery died. And one of the things that gets driven from the 12 volt supply on the board is the resolver amplifier. So the resolver exciter amplitude was dropping and dropping and dropping. And indeed, when I went and looked at it, low res amplitude. Battery charger back on. Cross fingers, everything else, push the throttle, spins perfectly. So that was ASC, and that was low 12 volt battery. So quite an adventure to get ourselves to the V3 board. But this is where we are at now, in that I have the board basically peppered with all of these links and situations. Now, one thing that I will just finally touch on, because this was, we're just circling back here to the beginning really, where we had a voluntary modification. One of the big problems that we had was that Open Inverter natively drives the resolver at 4.4 kilohertz, and that just wasn't the right frequency for driving the Model 3 resolver exciter coil. So we wanted to go to 8.8, and originally Johannes had given me a kind of a software kludge to do that with, but that software kludge was basically causing the processor to not have enough time to perform certain tasks like the parameter database and the CAN bus and stuff like that. So Dave came up with a way to use one of the spare hardware timers on the STM32 to generate that 8.8 kilohertz, and he basically did some magic in there to synchronize that timer that's generating the 8.8 kilohertz to the ADC capture trigger. So what we have now is a hardware driven resolver exciter waveform generator from the STM32, and that results in the microcontroller behaving perfectly normally. And as an added bonus, we have dropped our processor load when we're running and we're doing our gate SPI and our LIN bus and our CAN bus and all that. We're only using 42% processor load on the STM32. That brings me on to my next boring point, and that is, you know, some folks have said to me over time, and why am I not, you know, why am I using a STM32F103? Well, in this case, that's natively what Open Inverter always ran on from day one. And I'm kind of odd in my mechanism of doing things too, that if I have something that works, unless there's a compelling reason to change it, don't change it. Now, you can reasonably argue that, for example, an F405 or something like that that had a hardware floating point module in it would be a good upgrade, and I would certainly be perfectly happy to experiment with that if and when such a thing became available. But it requires a lot of work to get to that point. So that way, I decided for this board and for the MG board to go with the VCT6 100 pin performance line variant of the 32F103, and that's proven to be a good decision here, because that performance line part has got the pin count and extra hardware timers and stuff like that. That has proven to be very useful here with our resolver system, as I just described. So that's why we're going with the 103 here on this design. Some of you also had asked me or suggested that wouldn't it be much easier to reprogram the existing TI part on there. And if you want to look back a good few years now, you'll see some videos where that looked like the solution that was going to occur. Dave's been working on that, but despite my appealing to people and so on, and sending out various JTAG kits to people and stuff like that, nobody really wanted to participate in that. That leads me on, which is to hopefully the final point of this video here. You can also reasonably say to me that this is an incredible amount of work here, designing this and spending all the resource getting it manufactured, and, you know, screwing up, having to go back at it and make changes and keep going until the thing runs, build a car around it, for crying out loud. I don't know, I must be mad. When if I really wanted a Model 3 drive unit to run in a car, I could just pay a few grand to one of the companies that offer the CAN control system on the existing board and existing firmware. Now I've no problem with that. I'm sure it works fine. But I would not, I'm not here just to build cars, folks. I'm not one of these kind of personalities on here that just wants to build cars and, oh, look at what I've done, I'm so cool, and that's kind of never been my modus operandi here. I kind of want to promote understanding of things and also give people the knowledge to be able to work on their own vehicles and their own projects. Is the stuff that I come up with perfect? No, far from it. After a good few years now, and based on a large part of what I've learned here on the Model 3, I'm going back at designing the boards for the small and large drive unit, hopefully soon. But the reason that I'm doing this comes back to an initial feeling that I had again a good few years ago now, when Jack Rickard at EV and Anna Kloppenberg from New Electric sent me a Siemens motor and a DMOC inverter. I looked at this was like insane, because you could not get this stuff. And I remember I took the cover off the DMOC inverter, which was a huge thing. I looked at the boards in this, and you know, they're just stuffed full of surface mount parts, and they're all, you know, conformal coated and all this. I'm kind of looking at this and I'm thinking, okay, so I put this in my car and I drive down the road. What if that little part there fails? My car is going to stop. And how am I going to fault find this? Okay, how am I going to know it was that little part there that just failed, or had a bad solder joint, or whatever? You know, I can't get a circuit diagram, I can't get a board layout, I can't get a bill of materials, I have no fault finding information, there's no idea what kind of software is running on these chips. And that's what led me to Johannes. And that's why we're here now. That's why I'm still here now. Is because if I'm going to do something, then it needs to be something that folks can understand. That you can go to GitHub, you can download a schematic, you can download a board layout, you can get the software for the chip, you can get a bill of materials. You can go in there, you can look at it and say, okay, well, I should have this voltage here, I should have a connection from here to here. Oh, I don't have a connection from here to here. Oh, I've got a break. Now I can fix that, get back on the road. Okay, so that's why I pursue these solutions to things. Now you can say, well, oh, there's no need to do that, Damien. You just buy a new board, or do this, or do that. Well, that's up to you folks. Okay, you do whatever suits you. I won't be here promoting this thing with negative marketing. I'm just telling you the reason that I do these boards, in particular this thing, this way. So, alright, hopefully that will have bored you all completely away from me by now and put you to sleep. There's no cats even. My cats are under the bed quilt. They don't want to come out. This thing's gone cold, so we can get rid of that. So folks, that's it. The V3, it's just coming up to the end of September now when I'm filming this, 2025. I'm going to be ordering batch 10 V3 boards from JLC in about a week's time. And we will see then, hopefully, put our few parts on there, put them in the inverter, and it drives the Volvo for us. Fingers crossed. So, that's it. I hope you learned something, as Lewis would say here, from this crazy rambling random video. Hopefully the next time you see me with this board, it'll be in an inverter spinning motors and wheels in the car. Will ask you folks a question just from my own info. If any of you have knowledge or info on the parts of the circuit on the OEM board that's up around, let's say, the top right hand side of the board as you see it here, that relate to the ASC activation, then please get in touch, because I'd be quite interested just to know what the conditions are for activating that and what the logic is in the thinking behind it, just from my own info. I will not have that on these boards under any circumstance. Yes, I know what can happen. I have had inverters lose 12 volts when driving, so I do understand that part. Okay. That's it, folks. I know I'm just this has been a bit of a week. Let me thank all of you deeply for all the support, no matter what it may be. This board would not be here, would not be, you know, on the brink of ordering a first production batch without your kind assistance. So I will put a link in the video description to GitHub, where I will have a schematic and a board layout of this V3 up there for you, so you can have a look at it. Tell me what you think. So until next time, do check out that link. Ignore the ones to Patreon and PayPal and all that, because they're bad news. Giving me money is a big mistake, because then I spend it on these stupid projects until I have none, and nobody wants that. But yeah, that's it, and I will see you hopefully in the next fun-packed episode. And until then, happy ASC activation.